Hey gang, Mr. Gomez here again, and today we're going to be talking about the foundations of matter. So this might be a review to some of you, it might seem brand new to others, but no matter what, we need to get these concepts down before we can advance into more complex topics of chemistry. So, what is chemistry? Well, chemistry is the study of matter, be it solid, liquid, or gas, the study of matter, its properties, and how it interacts. So, how matter acts around other matter. So now we're going to take a very brief look at how chemistry got its start. And that goes all the way back to ancient Greece. In around 400 BC, a guy named Democritus first thought of the question, well, what if I took a piece of matter and I divided it in half? And then I divided it in half again, and so on and so forth. Would I ever get to the point where I could no longer divide that piece of matter in half? He said yes. Shortly after that, Aristotle came up with the idea that there's 4 classical elements. So his 4 classical elements, which wasn't unique to Aristotle, this existed in Asia as well, was fire, earth, air, and water. Some would argue that he added a 5th, ether, which is actually like vacuum, nothingness, if you will. But Aristotle's idea that there was 4 classical elements held true for a very long time. And that brings us to Antoine Lavoisier, a French chemist who is largely called the father of modern chemistry. He helped create the metric system, he helped study combustion reactions, he proved the law of conservation of mass for the first time, and he started to come up with this idea of what an element truly was, something that cannot be broken down into simpler forms. And he identified a few elements for the first time, those elements being hydrogen, oxygen, and sulfur, I believe. And then lastly, the last player in this brief history of chemistry's beginnings is John Dalton. John Dalton was an English school teacher, and he expanded on Democritus' atomic theory, and he came up with some postulates, some assumptions about the atomic theory. And so we're going to look at those next. So what John Dalton did was he took some of the ideas of an element and what an element was that Lavoisier wrote about, and he took that and he combined it with Democritus' atomic theory, and he wrote some basic assumptions of his new atomic theory, which still stands as the atomic theory. Now, consider that these are how he wrote them in his time, and may not all be true to this day. And so we'll talk about which ones we don't find true anymore and what that means for chemistry. But without further ado, the basic assumptions of atomic theory say an element is a substance, a type of matter, that cannot be broken down into simpler substances. That wasn't actually John Dalton who said that, that was Antoine Lavoisier who said that. From here on out, these are John Dalton's postulates of atomic theory. So these elements are made up of very tiny, indivisible particles which we call atoms. That comes from the Greek word for indestructible or indivisible. The atoms of a given element are identical in size, mass, and other properties. Atoms of different elements combine in whole number ratios to form compounds, and atoms will combine, separate, or rearrange in chemical reactions. Lastly, atoms cannot be created, destroyed, or subdivided. So how I like to think of it, and how we often refer to John Dalton's atomic theory, is the billiard ball model. So we have billiard balls, and each billiard ball, the 1 ball or the 2 ball or the 3 ball, those represent different elements. And you would say that 1 balls, regardless of the pool table you're playing on, all have a 1 written on them, and they're all yellow. So all atoms of this element, the 1 ball, are the same. And you can also picture that some atoms of some elements can rearrange, they can mix, they can mingle, and so you might have, for example, a compound that was 2 2-balls and 1 8-ball. And so that could be analogous to, say, water, H2O. So we've got to quickly pause and take a deep breath and recap on some essential vocabulary. We heard this in the last slide, but it doesn't hurt to hear it again. So, an element is a substance that cannot be broken down into simpler substances. And unique elements have unique properties. So all of the elements that we as a human race have discovered are organized in what we call the periodic table of elements, our best friend. So for example, an element would be oxygen. Probably all heard of the element oxygen. Now an atom is the smallest unit of matter that has the properties of that element. So we found out that there's actually smaller particles than atoms. They're called subatomic particles, and we'll hear a lot about them in just a minute. But subatomic particles don't have the properties of the element. So the atom is that smallest unit of matter that would look like oxygen, for example. So you can have atoms of oxygen. Next, a compound is two or more elements combined at whole number ratios. And lastly, a chemical reaction is a process that changes chemical compounds. So it could form them, it could destroy them, break them back down into elements, or it could just rearrange which atoms are bonded to which atoms. Now we did find out, after John Dalton, that there was a monkey wrench in his atomic theory. And that was with that last postulate, that last assumption that I read, that atoms can't be subdivided. Well, they really can, and atoms are made up of smaller particles. So we're going to study a lot in topic 4, quantum mechanics, the kind of structure of the atom and how the structure of the atom evolved through history. But for right now, know that subatomic particles are the particles that make up the atom, and there's 3 of them. My guess is you've heard of all 3 of these before, but we're going to just get the formal definitions of them out there and their properties. So keep in mind that a subatomic particle does not retain the properties of any element. They are just the properties of that particle. So a proton, for example, in helium and a proton in uranium would look exactly the same. So a proton is a subatomic particle. It's located in the nucleus of the atom with a mass of 1 atomic mass unit and a charge of +1. So when I say nucleus, I don't actually define this in this presentation, but a nucleus is the center. They're located in the center. And so a neutron is a subatomic particle that's also located in the nucleus, in the center of the atom. It's got a mass of 1 atomic mass unit as well, and a charge of 0. It does not have a charge. So when you hear neutron, think neutral, and when you hear proton, think positive. The last major subatomic particle, of course there's more than just these 3, but the last major subatomic particle is the electron. Now that's located outside of the nucleus, and what quantum mechanics really did, which we'll study in topic 4, is explain how the electrons exist outside the nucleus and what that looks like. But for right now, just know that an electron is a subatomic particle located outside of the nucleus. It has no mass. It does actually have mass, but for all intents and purposes right now, we're going to consider it as massless. And it's got a charge of -1. So electron is actually the thing that makes electricity happen. So electricity is a flow of electrons, and right there in that very common thing that we experience every day, we can see that atoms can be subdivided. So this is a picture of an atom. Now don't worry how they put the electrons on the outside of the nucleus, but know that here's your nucleus. Protons are in blue, neutrons are in red, and then electrons are green, and they fill out outside the nucleus. Lastly, we're just going to summarize. We're going to summarize these 3 subatomic particles. This is a very good chart to know and just have in the back of your pocket, if you will. So, we said protons have a mass of 1 AMU, an atomic mass unit. And actually, an AMU is defined as the mass of a proton. So it's no coincidence that it's 1. fun fact, an aside, in honor of John Dalton, another name for the atomic mass unit is a Dalton. So you could have, much like you can have a kilometer, you can have a kilodalton or a millidalton. A neutron also has a mass of 1 atomic mass unit. And I hope you picked up from this picture what we were saying before, that both the proton and the neutron live in the nucleus. So the nucleus is where all of the mass of the atom is contained, despite it being a very small volume of the atom. So thus far, the proton and the neutron look exactly the same. Where they differ is in their charge. So again, proton, I think, positive. It's a charge of +1. And with the neutron, I think neutral. Not negative, but neutral. So no charge. Lastly, that brings us to the electron. Keep in mind that up above we said the electron was massless. It does not have a mass. So we say it's got a mass of 0. And its charge was negative. It's -1. Also, the electron is not located in the nucleus, but rather outside of the nucleus. So note that charges can be canceled out. The charge of a proton can be canceled out with an electron and vice versa. Alright, so we're going to keep this table in mind as we move on through the next few slides. So here we come to the idea that subatomic particles really determine the element and the composition of an atom. So the first very important foundational thing to understand about atoms is that the number of protons within the nucleus of an atom determines what element that atom is. So the number of protons is also known as the atomic number. We use those two very synonymously, so you can switch them out. The atomic number is the number of protons in an atom. And the atomic number, or the number of protons, is what determines the element. So, an example of that would be, well, I have an atom with 6 protons. If it has 6 protons, therefore its atomic number is 6, and then I want to know what element that is. I'm going to have to look at the periodic table. I'll have to find which spot is referring to atomic numbers in each of the elemental blocks, which number refers to the atomic number, and I look for 6. And it turns out that carbon has an atomic number of 6. So carbon has 6 protons. Another one, for example, might be looking at neon. Now, neon has an atomic number of 10. Before I advance, make sure that's correct. It is. So I just checked the periodic table because it's a great resource. So, if I've said that my element that I'm talking about is neon, kind of running it in reverse now, then I know that neon's atomic number is 10. I get that from the periodic table. And I also know that since the number of protons is the atomic number, the neon also has 10 protons. All right, moving on. Another important property of atoms, of elements, that you'll find on the periodic table is the atomic mass. So the number of protons plus the number of neutrons of an atom is called the atomic mass. And that makes sense because if we look back to that table, we know that protons and neutrons are the only particles that have mass. So they're the only things that would contribute to the mass of an atom. So the number of protons plus the number of neutrons is the atomic mass. This is the mass in atomic mass units of the atom. So for example, if I have an atom that has 6 protons, and it has 6 neutrons, first of all, it's carbon again, right? 6 protons must be carbon. But its atomic mass would be 12, because 6 plus 6 is 12. And that's in atomic mass units or Daltons. Looking at another one, because protons and neutrons don't always have to be equal. So looking at another one, I could have 1 proton. If you're wondering who has 1 proton, you'd look at the periodic table and you'd recognize that hydrogen has an atomic number of 1, and therefore hydrogen has only 1 proton. But this hydrogen's special, because this hydrogen has 2 neutrons. And so the atomic mass of this particular hydrogen atom equals, no big surprises here, 1 plus 2 is 3 atomic mass units. And a good thing to note at this point is that we abbreviate elements as symbols. So you're probably familiar with this, but up here, I was writing out carbon and neon. Well, every single discovered element has a symbol. Keep in mind, chemists are lazy. So, if I wanted to write the symbol of carbon, I could use the periodic table, or I could just know it in my head. And so carbon has a symbol of C. Furthermore, you'll sometimes see, especially when talking about the composition of the nucleus, what's in the nucleus of an atom, you'll often see 2 numbers written to the left of carbon. And so the top number would be the atomic mass, the bigger of the numbers. So going on from this example where I had 6 protons, 6 neutrons, and an atomic mass of 12, if I were to write the elemental symbol so that it's describing atomic number and atomic mass, I would write in 12. The atomic mass goes on the top. And then on the bottom, I would write 6. So it kind of looks like a fraction. Don't draw a division sign. And keep in mind that the top number is atomic mass. The bottom number is atomic number. Just to do one more real quickly, I'm looking over here now. I have 1 proton, I have 2 neutrons. I'm saying nothing about electrons, by the way. 1 proton, 2 neutrons. And so my atomic mass is 3, but I also need to know what element this is. So I already said this is hydrogen. Hydrogen has an atomic number of 1. So I know I'm talking about hydrogen, and I use my periodic table to determine that hydrogen's symbol is H. H and nothing more. And I know that this particular hydrogen has an atomic mass of 3 and an atomic number on the bottom, of 1. The last thing I want to say about this is that not all elements have atomic symbols or elemental symbols that are only 1 letter. And so this is important because simply we have way more elements discovered than we have letters in the alphabet. So many elements have 2 letters as their symbol. Only the first is capitalized. So if I want to write chlorine, I look over there, I find chlorine symbol, it's Cl. And so I only capitalize the first, and I have a lowercase l, so make sure it's either got no tail or a very little tail. I've got a lowercase l. If I'm capitalizing the second letter, then I'm recognizing this as carbon plus some other element that has a symbol of capital L, which frankly doesn't exist. So it's very important that you only capitalize the first letter in an elemental symbol. So now we've arrived at another very important vocab word for the foundations of chemistry, and that's isotopes. So an isotope is an atom of a given element, therefore has the same atomic number and the same number of protons, but a different number of neutrons, and therefore a different atomic mass. Well, that atom is called an isotope. So best seen with an example. We recall from the last slide that we had a carbon atom with an atomic mass of 12 and an atomic number of 6. This is the most common carbon atom in the world. But there's other carbon atoms, and they don't differ in how many protons they have. They differ in how many neutrons they have. So the bottom number will stay the same. And then another common isotope, now I'm using the word, another common isotope of carbon is carbon-14. So its atomic mass now is 14. It's got to have more neutrons. And its atomic number is still 6 because it's still carbon. So you've probably heard of carbon-14 perhaps in carbon-14 dating. We use this isotope of carbon to determine the age of certain things. Now you might ask yourself at this point, so they have the same number of protons, but how many neutrons does each carbon atom have? Well, this one would have 12 minus 6. This one would have 6 neutrons. And this one would have 14 minus 6, so this one would have 8 neutrons. And that, of course, makes sense, that the atom with more neutrons is the heavier atom. This is the last thing I'll say about isotopes for right now, because this is important to understand when you look at a periodic table. The way we've defined masses right now is that the mass of a proton and the mass of a neutron, they're both 1. So the mass of an atom could only be a whole number. I can't subdivide a proton or subdivide a neutron. So the mass of an atom could only be a whole number. So while an individual atom can only have atomic masses that are whole numbers, the atomic mass on the periodic table are the weighted average of all of that element's isotopes. So if you look at carbon, you'll see its atomic mass is not exactly 12, but close to 12 on the periodic table. And that's telling me that the most common isotope of carbon is closest to 12. And if I grabbed a handful of random carbon atoms, the most ones I would get would be carbon-12, but it's slightly higher, so I would also get some carbon-14, just not nearly enough to bring that number up closer to 14. So now we're at ions. Ions are easy to confuse with isotopes. They both describe atoms and they both start with I, but ions are very different. So isotopes is concerned with the particles that give mass to the atom, the protons and the neutrons. Ions is concerned with the particles that give charge to the atom, protons and electrons. So it's very, very important to understand as we embark on this journey of chemistry that the subatomic particles that happen in a traditional chemical reaction, those which occur all around us every day, are the electrons. Protons and neutrons don't get transferred in chemical reactions. The elements that go in are the elements that come out, and in fact the isotopes that go in are the isotopes that come out. However, electrons in chemical reactions are either gained or lost by atoms. And so when an atom gains or loses electrons, when an atom gains or loses negative charge, it's going to take on some non-zero charge. So it could be positive, it could be negative, but whenever an atom is taken on a non-zero charge, we think of that atom as an ion. So keep in mind that when I refer to carbon 12 here, I'm making an assumption that it has 6 electrons. And that's because chemists will write the charge of the atom in the symbol, the charge of the elemental symbol, up here in the top left. And when there's nothing written, it's assumed to be 0. So if the carbon atom here has a net charge, total charge on the atom of 0, then it's got to have a proton for every one electron, or an electron for every one proton. Keep in mind, electrons have a charge of -1, protons have a charge of +1, so every one proton will cancel out the charge of every one electron. So if my charge is 0, and I've got 6 protons, boy, I better have 6 electrons. But let's consider a different atom. So this time, let's consider oxygen. Oxygen has an atomic number of 8. Therefore, I know it has 8 protons. But what oxygen will often try to do is seek out 2 electrons. And so if oxygen has done this in a chemical reaction, if it has gained 2 electrons and has 10 electrons, we know the protons and the electrons aren't equal anymore, and so it's going to have a non-zero charge, and be an ion. What is that charge, you might ask? Well, 8 of my electrons are canceled out with 8 of my protons, and then I have a leftover 2 electrons to give me a net charge of -2. So how would I write this? Well, I would write O, that's an O, not a 0, and that's standing for oxygen. And I would say that oxygen has a net charge of -2. Keep in mind, we write the charge up in the top right. Now, in this example, I haven't described at all anything about the neutrons, and so I'm not even going to make a judgment about what these 2 numbers are. Sure, I can say for sure that this is 8, because that's its atomic number. But I know nothing about the neutrons, so of this oxygen atom, I can't say anything about its atomic mass. You know, I'm just going to neglect them both. So I'm going to say this is an oxygen atom with 2 more electrons than protons, and therefore it's oxygen with a -2 charge. Let's see one more example real quick. Now look at sodium. So again, I gotta figure out how many protons does sodium have, regardless of who it's been reacting with. Sodium, I looked at the periodic table. Sodium always has 11 protons. If it doesn't, it's not sodium. But what sodium likes to do, as opposed to oxygen gaining 2 electrons, sodium likes to lose 1. So if we said that sodium had lost 1 electron, then sodium now has 10 electrons. Now I've got to ask, well, what is the net charge on sodium here? So sodium, Na, has 10 electrons to cancel out 10 protons. But then it's got that 1 extra proton. And that 1 extra proton gives it a +1 charge. Again, I know nothing about the neutrons, so I'm not even going to make a judgment about what numbers to write over here. But here is sodium ion with a +1 charge. Here's an oxygen ion with a -2 charge. Now for all of you algebra people out there who like to think of the world mathematically, we can write some algebraic expressions that help solve for these variables. So let's define some variables first. Let's let P equal the number of protons in an atom. Let's let N equal the number of neutrons in an atom. E equal the number of electrons in an atom. AN, capital AN, equal that atom's atomic number. Capital AM equal the atom's atomic mass. And C equal the atom's charge. Now before we write some equations, I just want to get this out there, that if I want to talk about any element's atom in the utmost detail, but do it very, very concisely. Do it as efficiently as possible. I can write a symbol to represent the element. So here I'm going to keep it generic, and I'm going to say the element's symbol is x. So x equals any element's symbol. And now that, of course, could be C for carbon, it could be H for hydrogen, it could be Cl for chlorine. Now we know that in the top left, we can write the atomic mass of that atom. In the bottom left, we can write the atomic number. And in the top right, we can write the charge. So this is a very efficient way to completely describe an atom. Because keep in mind, chemists are lazy. So let's write some equations using these variables. We'll start off nice and easy. If I wanted to calculate the atomic number of an atom, well, that's easy. It's just equal to the number of protons. So you could say AN equals P. Atomic number equals the number of protons. Right? Very simple, no big tricks there, no mathematical operations either. If I want to calculate the atomic mass of an atom, AN, I've got to consider what particles give mass to the atom. Well, that's the protons and the neutrons. So atomic mass equals P plus N. Right? Protons plus neutrons equals atomic mass. Now I'll solve these for each of the variables because that might be convenient for you. So if I want to know the number of protons, but I know the number of neutrons and I know the atomic mass, I could say P equals the atomic mass minus the number of neutrons. So just through algebraic rearrangement, I hope you can see how I got from here to here. And then lastly, neutrons equals the atomic mass minus the number of protons. Again, going from here to here is just algebra. The last set of equations I'm going to write refer to charge. So because neutrons have no charge, they're not going to show up in the equations, but I'm going to go through a quick derivation of what you will probably find to be a very nice equation at the end. So I want to know the charge of an atom. Well, the charge of that atom is going to be equal to the number of protons times the charge of each individual proton, that being plus 1. And then that is going to be equal to, or excuse me, that is going to be added with the number of electrons times the charge of each individual electron, right? And when P and E are equal, the charge is 0 because all of the P's cancel out all of the E's. So if I simplify this, I can get to charge equals protons minus electrons, right? That -1 is distributed over. And this equation will always give you the right charge given the number of protons and the number of electrons of an atom. And it'll give you the right charge, positive or negative, too. Because if E is greater than P, I'm going to get a negative number. That makes sense. And if P is greater than E, I'm going to get a positive number. That also makes sense. So if I were to rearrange this equation, I could say that P equals, I'm going to add E to both sides. Well, P equals charge plus the number of electrons. So given the charge and given the number of electrons, I can calculate P. And then lastly, E, well, if I take this equation I just made and I subtract C from each side, E, the number of electrons, equals P minus C. All right, so these equations for determining atomic mass and for determining a charge are very important as you start to play around with it. So now I just want to get out there the systematic way that we write about compounds. So we write about compounds by using elemental symbols, that which you find on the periodic table, and subscripts, so numbers written down at the bottom right of the elemental symbol. So a subscript tells you how many atoms of the element that comes before it are in the compound, before it being the subscript. So a very common example we've probably all heard of before is H2O. So that's a compound. It's water. We need it to stay alive. And if I want to think about water in terms of what elements make up water, well, I know that there's hydrogen and I know there's oxygen. Furthermore, I know there's 2 atoms of hydrogen and only 1 atom of oxygen. So there's 2 atoms H plus 1 atom O. Now, how did I know there was 1 atom of oxygen? Well, no number's written here. So I can assume it to be 1. It's one of the many invisible ones in the world. So really, you could write this formula as H2O1, and it's essentially meaning the same thing. It's important to note that the subscript is talking about the number of atoms of the element that comes before it, not after. So let's look at another one of these examples. Let's look at what makes up bleach. What makes bleach bleach? That's HClO3. So again, if I just want to look at this compound formula of this compound, and I want to determine how many of each element, how many atoms of each element are in this compound, I can say that right off the bat, I'll just write in the invisible ones. There's 1 hydrogen, there's 1 chlorine. Just keep in mind, Cl, since the L is lowercase, is just 1 element. It's chlorine. And there's 3 oxygens. So I've got 1 hydrogen atom. I've got 1 chlorine atom. And I've got 3 oxygens. Now I'm going to define one more word, and it's a word I'm sure we've all heard before. The smallest unit of a compound is the molecule. And so it's akin to thinking of the smallest unit of an element is an atom. Well, the smallest unit of a compound is a molecule. The molecule is the smallest piece of matter that retains the properties of that compound. The last curveball we got to throw at you real quick is this idea of parentheses, because parentheses show up in compounds, so we might as well just get it out on the table right now. So let's consider a formula such as CaNO3 2. So here I have NO3 in parentheses with the 2 on the outside, and I've got to know how to interpret this so that I can determine the number of atoms of each element in this compound. This is called calcium nitrate, by the way. So how many atoms of each element are in this compound? Well, Ca is a player outside of the parentheses, so he's just by himself, and furthermore, he's got no subscript after him, so I'm going to assume it to be 1. So I have that 1 atom of calcium. But then I've got to ask myself, how does this 2 affect this NO3? So you could write this just the same as saying I have 2 NO3s. So it's not additive, but it's multiplicative. So think of distribution. I have 2 of everything within the parentheses. Maybe it helped to write this in its expanded form. Ca, and then I have 2 NO3s. So I have NO3, NO3. Now know that N is nitrogen and O is oxygen. NO is not its own element because they're both capitalized. So I have Ca, NO3, NO3. And if I were to group that, I would say I have Ca, N2O6, right? There I'm just grouping that I have 3 oxygen atoms and 3 oxygen atoms, and I have 1 nitrogen and 1 nitrogen. Another way you could think of this is, like I was saying before, use the distributive property of multiplication. Assume you're 1 after nitrogen, and know that 1 times 2 is 2 nitrogen atoms. 3 times 2 is 6 oxygen atoms, and you arrive at the same answer in the end. So I have 1 atom of calcium. In total, I have 2 atoms of nitrogen, and I have 6 atoms of oxygen. All right, moving on. So here's just some additional vocabulary to throw out at you. When we mix compounds, we get a mixture. And those mixtures can be either homogeneous or heterogeneous. So a homogeneous mixture is a mixture where the compounds are evenly distributed throughout. So think of homogenized milk. It looks pretty even throughout, and that's because it's a mixture of water and milk fats, evenly distributed. And then a heterogeneous mixture is a mixture where the compounds are unevenly distributed throughout. So here, you can see a piece of granite, and the granite has these areas of dark color and areas of light color that make it so beautiful, but in that, it's telling me that there's areas where there's more of one compound than other areas. And that gives that dark color in some spots, the light color in others. So this is another very special type, very important to chemists type of mixture, and that's called a solution. So, a solution is a homogeneous mixture, it's even throughout, where you take a solute, some sort of compound, and you dissolve it in a solvent. So the solution will then take on the properties of the solvent. We've all made solutions, I guarantee it. One example of a solution would be putting salt in water. The water dissolves the salt, and so you could think of the salt as the solute, and the water as the solvent, and you get a solution that takes on the properties, more or less, of the solvent. Another example would be putting sugar in your coffee. So this brings us to one of the more challenging concepts of this lecture, and that concept is the mole. The mole is very, very important to chemists, and the mole is used as a counting unit. So the mole is a unit that's used to count things. What do chemists like to count? Well, they like to count particles, be them atoms or molecules, protons, neutrons, ions, what have you. They like to count particles. So the most two common things that will count will be atoms and molecules. So I like to think of the mole much like the dozen. So if I say I have a dozen eggs, well, I have 12 eggs. The mole is just like that. It's a counting unit. And if I say I have 1 mole of water, then I have 6.02 times 10 to the 23rd particles, in this case molecules, of water. So this number, 6.02 times 10 to the 23rd, is actually known as Avogadro's number. It's named after another scientist named Avogadro. So we can take this bold underlined sentence and we can write it as a very, very important conversion factor to chemists. So if I take this, I can say that 1 mole of anything, it could be molecules of water, it could be atoms of carbon, it could be protons, 1 mole per 6.02 times 10 to the 23rd particles. Now that's one of the conversion factors I can extract from this bold underlined sentence. Another one would be flipping it, the reciprocal. Well, there's 6.02 times 10 to the 23rd particles per 1 mole. So I'd want to use this conversion factor if I'm trying to cancel moles and get into particles. And I'd want to use this conversion factor if I'm trying to cancel particles and get into moles. Alright, lastly, and as we already said, that particles can mean any number of things. I could count a mole of eggs like I use a dozen for eggs, I could count a mole of eggs. I just have a lot of eggs, or an absurd amount of eggs. So we count really small things with the mole. Things that you can have a lot of, but it doesn't look like much of. And so particles are those small things, such as atoms, molecules, protons, electrons, etc. We use the mole to convert between the microscopic world, all these little small, almost undetectable particles. We use the mole to convert between those small particles in the macroscopic world, the world we see every day. So another very important concept to chemists is the idea of molar mass. So the molar mass of an element or a compound is the mass in grams, so the mass expressed in grams, that 1 mole, also known as 6.02 times 10 to the 23rd particles, of that element or compound weighs. So I can find the molar mass of carbon, and that's the number of grams that this many atoms of carbon weighs. Or I can find the molar mass of water, and that's the number of grams that this many molecules of water weighs. So the molar mass of an element is equal to its atomic mass, found on the periodic table, but expressed in grams. For example, if I take oxygen, which depending on the periodic table you use has a atomic mass of either, some round it to 15.99 atomic mass units, others round it to just 16 atomic mass units. So we'll go with 16 for this. An atomic mass of 16 atomic mass units. Then I can say that the molar mass equals 16 grams. In which case I can then use this concept as a conversion factor. I can say that I have 1 mole of oxygen per 16 grams oxygen. Or conversely, I can write the reciprocal. For every 16 grams oxygen, there is 1 mole of oxygen. So again, you'd use this conversion factor to go from grams to moles, and you'd use this conversion factor to go from moles to grams. And then once you're in moles, you could take that even further, use this conversion factor and get to particles. So I could find a mass of oxygen and through these 2 conversion factors determine how many atoms of oxygen are in that sample. Pretty powerful stuff. It gets a little more complicated when we start to look at compounds. So in a compound, the molar mass in grams, still expressed in grams, of a compound is equal to the atomic masses of all of the atoms that make up the compound. So let's start off with looking at water. H2O. Well, I've got to ask myself, how many atoms do I have and of what elements? I have 2 hydrogens, 1 oxygen. So what's the atomic mass of hydrogen? Well, the atomic mass of hydrogen, referencing the periodic table, is, for all intents and purposes, let's say 1.01. Depending on your periodic table, they round differently. Atomic mass units, it's the atomic mass of hydrogen. So I have that 1.01 for 1 hydrogen atom, but I have 2. So 1 and then another. So I need to add that second hydrogen atom on, 1.01 atomic mass units, plus I've got the 1 oxygen atom. So I've got to add that on as well, which we said up there was 16 atomic mass units. So in the end, I would say this whole molecule, the molecular mass of water, is 18.02 atomic mass units. Now that's the molecular mass. So the molar mass is the same number but expressed in grams. So 1 mole of H2O, or 6.02 times 10 to the 23rd molecules of H2O, is equal to 18.02 grams of H2O. Now, I remind you again, once you have parentheses in the mix, you've got to account for all the atoms that make up the molecule. All of the atoms add weight. So make sure that you're distributing that number outside the parentheses appropriately. If I were to take this equality, 1 mole of water equals 18.02 grams of water, well, I'd write it as a conversion factor like this. 1 mole H2O. Sometimes we drop the E and we abbreviate mole, just MOL, per 18.02 grams H2O. Or I could write the reciprocal, of course. 18.02 grams H2O per 1 mole H2O. So those are two conversion factors true about water that you could use to convert between grams and mole. Alright, so this brings us to mole conversions. These are the idea of using Avogadro's number and molar masses and being able to convert between grams of a compound, or grams of an element, and moles of a compound, or moles of an element, and then number of atoms or number of molecules. Very, very important to chemistry. Will come up over and over throughout the semester. So, I'm going to just show you an example, and then the best way to learn about mole conversions is to practice your dimensional analysis and then use it when you're actually practicing mole conversions. So let's write a question real quick. How many grams of water are there in 5 moles of water? It's a fair question. I want to know, how much does 5 moles of water weigh? Well, I wrote from the last time that there's a conversion factor that says there's 18.02 grams H2O per 1 mole H2O. So then I'm just going to run through my same procedure for dimensional analysis. And I identify my desired. I want to get into a unit of grams of water. And I'm going to identify what's given to me. I'm given 5 moles of water. And I think you'll see that this isn't a far leap from what we were just doing. The idea, the trickiest part, is using the periodic table to determine your own conversion factors for these. So, I write my grams H2O, and I want to find what number goes here that equals 5 moles H2O. And I've got to have a conversion factor. Now luckily I wrote my conversion factor right the first time because I have moles in the denominator. So since I have moles in the numerator here, I can have moles in the denominator here. And we know that mole over mole cancels out. And I want to get to grams, so I write grams in the numerator up here. My given is canceled away and I'm left in grams. So then once my units are written in the right spots, I can just fill in the numbers. And I know that there's 18.02 grams per 1 mole of H2O. Lastly, I've just got to do the calculations. 5 times 18.02. Comes out to be 90.1. So 90.1 grams of H2O is how many grams of water there are in 5 moles of water. Know that I could take this same question, and if I wanted to go instead from moles to grams, I wanted to go from moles to particles, or moles to molecules, I would just use Avogadro's conversion factor instead of the molar mass. And so here's a nice little roadmap to show you how you can use molar mass and Avogadro's number to convert between grams, moles, and number of particles, molecules or atoms. So this over here represents particles. And we'd use this roadmap like this. We recognize that we're given grams and we want to go to moles. So the arrow is pointing from grams to moles, so therefore we must divide by the molar mass. On the contrary, if I want to go from moles to grams, I've got to multiply by the molar mass of that compound. Keep in mind, these numbers change depending on the compound you're talking about. A mole of hydrogen gas does not weigh the same as a mole of water. If I want to go from moles to number of particles, again, the arrow is pointing from moles to number of particles, so I multiply by Avogadro's number, 6.02 times 10 to the 23rd. If I want to go from number of atoms or number of molecules, particles, back to moles, I would divide by Avogadro's number. Now, if I want to go from grams all the way over to particles, I've got to go through moles. So the first thing I do would be divide by the molar mass, and then the next thing I'd do would be multiply by Avogadro's number. Say I want to go from number of molecules, number of atoms, particles, what have you, all the way back to grams. Well, the first thing I'd have to do would be divide by Avogadro's number, and then I could multiply by the molar mass. And so this is a helpful way of showing you what dimensional analysis will tell you to do in the end, but this could be a little convenient roadmap for some. So here's the very last thing I want to talk to you about, and this is chemical reactions. So just so you understand the systematic structure of chemical reactions so that I can show them throughout the semester. I'm not asking you to do anything overly complex with them right now, but just so you get the general structure. So we write chemical reactions very systematically. We use a kind of structure like this. So I would read this as compound made of A and B, elements A and B, which aren't actual elements, they're keeping it generic. A compound plus some element C reacts to form, the arrow is read as reacts or yields, some compound AC plus some element B. So you can see in this example that I used to show you about the structure of chemical reactions, you can see that really what's happening is C is taking B's place in this compound with A. So it doesn't always have to be some compound plus some element. It could be some compound plus some other compound yields, and then maybe B and D switch spots. So I'd get AD plus CB. Point being that the compounds or elements that go into the reaction, the things on the left side of the yield sign, are called the reactants. So we call what is over here the reactants. They go into the reaction. And then the compounds or elements that come out of the reaction are called the products. They are produced. Lastly, it's important to know that the arrow separates the before and the after, and the arrow is called the yield sign. So you could say the reactants yield, produce the products. So reactants yield products. That's pretty much the simplest structure I can give you for how we write chemical reactions. So I'll quickly show you an example. We have HCl, a compound made up of hydrogen and chlorine, and that's going to react with NaOH. So this is a compound made up of sodium, oxygen, and hydrogen. Now in this particular case, we have some rearrangement going on. Don't worry too much about where or how the rearrangement happens, but know that we produce products. So these products happen to be water, H2O, and in fact, this H joins up with that OH and makes H2O, plus NaCl, salt. So here is an example where we have some reactants. They combine, they mix, they mingle, they yield some products.